This video presentation aims to teach the student the typical process control system, its elements, as well as the simple derivation of the transfer functions governing these elements. Block diagrams and the actual pictures of these elements will also be presented. This figure is the general outline of a control system. The controlled system has an input variable and an output variable. Its response is described in terms of dependence of the output variable on the input variable. These responses between one or several variables can normally be described using mathematical equations based on physical laws. The advantage of creating a system with an input and output variables representing the entire system as a block is that this representation separates the problem from the specific equipment used and allows a generic view. A closed-loop control system is a process where the controlled variable is continuously monitored and compared with the reference variable. Depending on the result of this comparison, the input variable for the system is influenced to adjust the output variable to the desired value despite of any disturbing influences. This results in a closed-loop action. Let's take a look at the agitated heating tank system. This is also an example of a first-order system. The temperature of the outlet stream, which is the output variable, is to be maintained at a predetermined value known as the reference value, or simply called the set point. First, a measurement is made using a thermocouple. This measurement is converted into an electrical signal with the aid of a transducer. This signal is passed to the controller and compared with the desired value. Comparison takes place by subtracting the measured value from the desired value. The result is then the deviation, or simply the error. In order to automatically control the control valve with the aid of the deviation, an electrical actuating motor or a converter is required. This allows adjustment of the controlled variable. This part is then called the manipulating element. It is important to understand that the basic parts of any control system will have the same names and provide the same functions, regardless if the controller is a pneumatic or a microprocessor-based system. The block diagram shows the basic parts of the control system being stated earlier. A typical control system is composed of the process or the controlled system, the measuring element, the controller, and the final control element. The process or the controlled system is the part of a machine or plant in which the controlled variable is to be maintained at a desired value and in which manipulated variables compensate for disturbance variables. Input variables to the controlled system include not only the manipulated variable but also disturbance variables. Let's consider first the block for the process. Let's do an unsteady state energy balance around the tank. we have your energy in minus energy out equals the accumulation in the tank. We have Q plus WC Ti minus To minus WC T minus To equals raw CV dt over dt. Here, the To is your set point. At steady state, d capital T over dt is equal to 0. The equation can then be written as Qs plus WC TIS minus To minus WC TS minus To equal to 0, where the subscript S has been used to indicate steady state. The two equations can then be subtracted. Notice that the reference temperature To cancels out in subtraction. This time, deviation variables can then be introduced. By doing the mathematics, this equation can then be obtained. From here, a Laplace transform must be done to this equation. Hence, we obtain T prime S times rho V over W S plus 1 equals Qs over Wc plus TIS. The expression rho V over W can then be substituted into tau. Simplifying these equations, we are able to obtain a transfer function. If the change is in Q only, then your Ti prime will be equal to 0. Hence, the transfer function relating to T prime to TQ is then T prime S over Qs equals 1 over Wc over tau S plus 1. In another case, if there is a change in T only, then Q is equal to 0. The transfer function is then equal to 1 over tau S plus 1. This is a transfer function relating T prime to Ti. In order to make the controlled variable accessible to the controller, it must be measured by a measuring element. This can either be a sensor or a thermocouple. The measured value is then converted into a physical variable that can be processed by the controller as an input. This measuring element may also exhibit a dynamic lag. For this example, our measuring element is a thermocouple, or any temperature measuring element. Let's assume that this element is a first-order system, for which the transfer function is equal to T prime S over T prime S equal to 1 over tau M S plus 1, where the input-output variables T prime and T prime M are deviation variables. Your Tm is the measured temperature, and your T is the desired temperature. The controller has the task of holding the controlled variable as near as possible to the reference variable. The controller constantly compares the value of the controlled variable with the value of the reference variable. From this comparison and the control response, the controller determines and changes the value of the manipulating variable. For convenience, the blocks representing the controller and the final control element are combined into one block. In this way, we are concerned only with the overall response between the error and the heat input to the tank. Also, it is assumed that the controller is a proportional controller. The relationship for a proportional controller is equal to Q equals Kc epsilon plus A, where the epsilon is your error, which is equal to your set point minus the measured temperature. Kc is the proportional sensitivity or the controller gain. A is then equal to the heat input when your epsilon is equal to 0. Knowing that the entire equation is equal to A at steady state, we are able to obtain the equation Q is equal to Kc epsilon. From here, a Laplace transform is obtained, which is simply equal to Qs is equal to Kc epsilon s. Hence, a transfer function is then obtained. We have Qs over Es, or your epsilon s, equal to Kc. Take note that this transfer function is only applicable when your controller is of the proportional mode. Now that we have obtained the transfer functions for the different elements, we can now substitute these transfer functions to the block diagram presented earlier. This block diagram clearly shows the relationship between the input variable, the elements, and the output variable. With the aid of this block diagram, one can easily predict or know when and how the error in the process will occur.